Now, you can be given questions where you know what the K value is for a reaction. So let's take iodine gas, vaporized iodine, and turn it into vaporous monoatomic iodine, which is balanced for I2 breaks down into two I gases. We know the K value. We know the initial concentration of the iodine. The question can be, find all the equilibrium concentrations. Woo! Okay. You have to set up the box we did before with initial, change, and equilibrium. ICE. Some people call it the ice box. Now, when you get the ice box all done here, you'll be able to plug into the expression. Let's go through it. Well, the implication is if we have 0.2 moles per liter of this, we have none of this to begin with. So if the chemical's not even mentioned as having a concentration, it's zero. Now, what do we have to do? Well, we have to make something here and lose something here in order to get to equilibrium. So we have to lose from here, and we lose x here because there's a 1 in front, so it's a 1x. But what do we gain here? We take the coefficient in front, put it in front of x. We gain 2x here. And so at equilibrium, we add the lines together. 0.20 minus x is the concentration of the I2 at equilibrium. That makes sense, doesn't it? And this is going to be, well, 2 times whatever x is. Plug it into the expression. Here's the expression. I squared divided by the I2. The k is going to be 2x, and it's going to be squared, divided by 0.20 minus x. And we know what that k value is, so we don't even write k, we just write 3.8 times 10 to the negative 5. So, look what we're looking for, x. And once we find x, we'll be able to substitute it into this line here. See the equilibrium line? We can put 2 times x there, that's the concentration of that at equilibrium, and 0.2 minus x is the concentration of that at equilibrium. So it's going to work out just nicely. But you know what? 2x squared is actually 4x squared, isn't it? 2x squared is 4x squared. Oh boy, x squared, an x term, and not, oh man, are we going to have to rearrange this and do quadratic formula? Not until disc 3. But here's the thing. There are ways of being able to do this question, a little sneaky, but you know what? It's understanding what math is all about, okay? Now here's the thing. You know what that k value is suggesting here? Remember we talked about this before. With a very, very small value of k, you don't make a heck of a lot of product. So 2 times not a heck of a lot is actually going to be not a very big number. And that very small, small number, which is what x is going to be, because the k value is so small, taking it away from 0.2 is essentially going to still give you, to 2 significant digits, probably 0.20. Oh sure, something's going to be lost here, but this concentration might end up being 0.19995. Well, to 2 significant digits, it's still 0.2. You know what you can do? Anytime x is added to or subtracted from a number, you have the ability to perhaps disregard that x if the k value is low enough. How do you know that? If you take the initial concentration of 0.2 and divide it by the k value, so 3.8 times 10 to the negative 5, if you get a number that is going to be here greater than or equal to 1,000, that's what we call, it's essentially called the 5% rule. But here's the thing. If you get initial concentration divided by k greater than or equal to 1,000, you can disregard x in a calculation when it's added to or subtracted from a number. Oh baby, what does that mean for this? It means that this x here is irrelevant. It's going to be too small to make a difference. And by the way, that number is greater than or equal to 1,000. It's really, really large. So when we do the math here, you actually get 4x squared equals, now it's going to be this number, it's just 4x squared equals this times this. We multiply each side by 0.2 now that this is gone. And then you get here 7.6 times 10 to the negative 6. And so when you do that math there, x equals 1.4 times 10 to the negative, and it better be 3, and of course it is, 10 to the negative 3. That's the value for x. Cool. So that's our answer. No, you got to be careful. That's not the answer. The question was to find the concentrations of these chemicals at equilibrium. So the concentration of the I at equilibrium equals 2 times X, which is 2 times 1.4 times 10 to the negative 3, which of course equals 2.8 times 10 to the negative 3 moles per liter. Now that's when we put the concentration back in the unit. And then the concentration of the I2 that's left over is 0.20 minus that X value, which is 1.4 times 10 to the negative 3. And you know what? Just like we said, if you subtract that from that to two numbers after the decimal, you still get 0.20 moles per liter. It didn't change very much, but remember, it did. It lost a little bit to make a little bit here to give us a K value that's very small. Whew!